All right, so today we're going to look at some integration techniques with the natural log function. So because the derivative of ln of x is 1 over x, then we can also work in reverse. All right, it should work in reverse for taking integrals. And it does. The integral of 1 over u du is equal to ln of u plus c. All right, so what we can do is we can go to work on these problems. So let's look at the first example that we have is we just have 4 over x dx. All right, so anytime I see an x in the bottom, or anytime I see a jumbled bunch of stuff in the bottom of a fraction, I can automatically think of that as a natural log type function. All right, so I know that this one is just going to be 4 ln of x plus c. And that is what that one integrates to be from our pattern from above. Okay, look at number 2. So we have 4 all over 3 minus 6x dx. Okay, so what I want to do is I'm going to convert this problem into be something like a 4 over u du type problem. All right, so in order to do that, we need to do some u substitution here. So I'm going to let u be 3 minus 6x. So my du dx is going to be negative 6. And now when I solve for dx, I get negative 1 over 6 du. Okay, so that's going to help me out here. This is really like 4 integral 1 over u times negative 1 over 6 du. All right, and this is coming from the dx, which is being plugged in here. All right, so what is that? That's really negative 4 over 6, which simplifies to be negative 2 over 3 when we take care of that. And now the integral of 1 over u is just going to be the ln of u plus c. All right, we have the ln of whatever our u is, all right, and that's 3 minus 6x plus c. So this would be our final answer right there for that second problem. Okay, so let's look at number 3. We have the integral of 7x over x squared plus 4. All right, and so first thing that I'm thinking about is I'm thinking, I have something all over something, so I think I'm going to have an ln somewhere in my problem. I also think that I might need to use some u substitution here. So I'm going to let u be equal to x squared plus 4, so my du dx is equal to 2x over 1. So there, my dx is equal to 1 over 2x du. Okay, so how does that help me out? Well, I'm allowed to take 7x over u times, now dx is actually 1 over 2x du. Well, you notice here that my x's cancel, and we can take this 7 over 2 and bring it out front. And now we're just left with the integral of 1 over u du. And that is very, very nice and easy to take the integral of. So we're left with 7 over 2 ln of u plus c. All right, and we can plug back in for what our u was, which was x squared plus 4. And so that is our final antiderivative there for number 3. Okay, let's check out number 4. We have the integral of tangent x dx. Okay, so a couple things that we can look at here. We have some rules that we could look at. I also know that tangent is the same as sine x over cosine x. Okay, so I do know that. All right, that's going to kind of help me out as I'm going through some of this. I'm going to let my u be equal to cosine x. Okay, and our du dx is negative sine of x. So what do we get? We get dx equals negative 1 over sine x du. Okay, so let's see what happens here with our problem. We have the integral of sine x over u. Then dx turns into negative 1 over sine x du. And nicely enough, just like last time, our sine x's cancel. We can bring that negative 1 out front of everything. All right, and that gives us the integral of 1 over u du, which is going to go to be negative ln of whatever u is plus c. So negative ln, our u was actually cosine of x plus c. And that would be our final answer there for number 4. Okay, so let's move on. Let's kind of look at some other types of examples and see what's going to happen on these. So look at number 5. On number 5, you have cosine of 2x on top. In the bottom of our fraction, we have 2 plus sine of 2x dx. All right, so kind of like I normally do with my u substitution, I'm going to let that whole bottom of the fraction be my u value, because we know that we really want something cosine over 2x over u, and then we're hoping that maybe the cosine of 2x might cancel with whatever our du dx is. Okay, so let's look, see what happens here. So u is 2 plus sine of 2 of x. Okay, Now let me take du dx, because that's what we always do when we look at our u values. All right, so 2, that goes away. The sine of 2x is the cosine of 2x times the inside, which is just 2. So really that is, let's go, dx is equal to, we have 1 over 2 cosine 2x. All right, and then that is in terms of du. Okay, so that helps me out. Let's look. We got 1 over 2 cosine 2x du. Okay, so, oh man, that's awesome. We did get something to cancel. Man, it's exactly what I wanted. The cosine of 2x cancels with the cosine of 2x. I can take this 1 over 2 and bring it out front of my fraction, out front of my integral. All right, we have 1/2 1 over u du. Oh my goodness, look how nice and easy this turns into be. All right, this is 1/2, then this is ln of whatever u is plus c. And our u is just 2 plus sine of 2x. Man, that's awesome. I love that. Great problem right there. All right. Let's keep going. Let's look at number 6. Okay, so example 6 in our notes. All right, we have the integral of 1 over cosine squared x plus tangent x. Okay, dx. I'm going to do a little bit of manipulation here, and I'm going to change 1 over cosine squared. I'm going to change that to be, that is actually the secant squared of x all over the tangent of x dx. Okay? Now that I know that, let's see, how might that help me? Well, I know that if I let u be tangent, I need something to cancel with secant squared. Well, if I take the derivative of u, isn't the derivative of tangent secant squared x? I think that it is. So now when we get dx, I have 1 over secant squared x du. Oh, I think that's going to work. Oh, let's try that. All right. So you have secant squared all over u times dx actually becomes 1 over secant squared x du. Hey, that's what I'm talking about. Let's go. All right. And look what cancels. Well, look at that. All that junk cancels. I'm left with 1 over u du. So this one is ln of u plus c. And here my u value happens to just be tangent x. Man, that one worked out nicely. But it was just from kind of doing some tricks. Okay, so I had to figure out a little trick to help me out. And that trick was changing 1 over cosine squared to just be the secant. All right, let's look at number 8. So here I have ln of x raised to the 4th power over x. And we're trying to take the antiderivative of that. So what I'm going to do is I'm going to let u be equal to ln of x. So if we take our derivative of u, we know that the derivative of ln of x, is 1 over x. Okay, so we solve for dx. That gives us x over 1 du. Okay, so let's look at how that would plug back in. So we have u to the 4th over x times dx is actually x over 1 du. Well, look at that. I have x and x will cancel each other out. And now we're just taking the anti-power rule of u to the 4th du. And that one actually turns out to be pretty nice. So we have u to the 5th all over 5 plus c. So my actual antiderivative here is ln of x to the 5th all over 5 plus c. Okay. Let's move on to look at some different examples with e to the x. So I want y'all to move on down to number 13. On 13 we have the integral of 4e to the 5x. All right, so since we know that the derivative of e to the x is e to the x, the same has got to be true with its integral. The integral of e to the u is actually e to the u plus c. All right, so we're going to use that as we're going through these problems. So what I'm going to do is I'm going to allow u to be 5x up here. It's usually what's in that parentheses. So du dx is 5 over 1. And so when we solve for dx, we get 1 over 5 du. Okay, so we're looking at kind of that pattern that's going on here. So I'm going to bring my 4 out front. I have e to the u dx, so now times my dx is actually 1 over 5 du. And so this is going to give us 4 over 5 integral of e to the u du. We know that the, what do I take to get e to the u as my derivative? Well, that's just e to the u. So we have 4 over 5 times e to the u plus c. And now we just plug back in what is u. So e to the, our u was 5x plus c. And that is our final answer for the antiderivative of that. Okay, let's look at, say we have one like, let's say number 16. Okay, I've got cosine of x times e to the sine x. All right, let's see how that works out. Okay, this is all in terms of dx. Remember, I'm going to try to choose something wisely. So I can think of that sine x to be in parentheses. Let's try u is equal to sine x. So just like always, I'm going to take my derivative of u with respect to x. So the derivative of sine is cosine x. So now kind of do some flipping around to solve for dx. That gives me 1 over cosine x du. And that's just from multiplying both sides from dx. Or excuse me, multiplying both sides by dx and then doing some division, just solving that equation. So how does that help me? I have the integral of cosine of x times e to the u times dx is 1 over cosine of x. du. So now my cosine x's cancel, and we're just left with the integral of e to the u du. And we know that e to the u, when you take the derivative of that, you get e to the u as well. So this is just going to be e to the u plus c. So we have e to the sine of x is u plus c. And that would be our final answer. Okay. Maybe let's look at one more of these. Let's try something like I don't know, maybe 18. 18 looks like a doozy. All right, so let's try that bad guy out right there. We have e to the x plus e to the negative x all over e to the x minus e to the negative x. Ooh, man, what to do? That looks pretty bad. Huh. Well, I know that when I have some fractions, I know that we have usually taken our u to be what's in parentheses, or maybe what's in the bottom of the fraction, like going back to number 5. Didn't we let our u be the bottom of this fraction? Okay, I think we did. All right, bottom of the fraction here. I think we did. Okay, that one was simple, but it was the bottom of the fraction. So that tends to be a pattern that seems to emerge a little bit in these types of problems. So I'm going to let my u be the bottom of this fraction. So we're going to let u, this is in terms of dx, we're going to let u be e to the x minus e to the negative x. Okay, we're going to take the derivative of u with respect to x. So e to the x is just e to the x minus e to the negative x times negative 1. Well, what is that? Du dx. This actually simplifies a little bit. That's going to be e to the x plus e to the negative x. Okay. Do some simplification around. So let's flip everything. That's 1 over e to the x plus e to the negative x du. Oh man, what do you know? Isn't that going to cancel? Isn't this going to cancel with the top? I think that it does. So we have e to the x plus e to the negative x over u times 1 over e to the x plus e to the negative x du. And lucky for us, because of how we picked our u, we get that to cancel, which is exactly what we want. So we're just left with the integral of 1 over u du, which turns out to be a very nice and easy thing to take. We know that that's just ln of u plus c, and u was e to the x minus e to the negative x. And so that one would be our final answer there. So really not too bad. You just have to know where to start and kind of where to go from there.